All right, happy week 10, everyone. Let's begin. A bunch of logistics stuff to go over first. So today we'll do two things in class, a little bit from 4.6. I'll do an example, then you'll do an example. And the example that you'll do is actually essentially your homework problem from 4.6, so some added incentive. And then I thought it might be useful to spend a little bit of time reviewing some stuff from Chapter 3. I've been in the midst of doing lots and lots of grading, and there are a handful of mistakes that I'm seeing coming up a few times. So I thought maybe we can review a few of those and do sort of like a warm-up for the final. So I'll say more about that in a sec. All right, so homework help. I'm available today after class. I have a meeting at 3 down in Turrets that I don't want to be late for, so I should probably leave at about 10 of or 5 of or something. But that should be enough time to get people through some stuff. Tomorrow, I've got kind of a full day, but can do homework help 5 to 6. I might be free before 5, but I'm not 100% sure what my afternoon looks like. Wednesday, for sure, 4:30 to 6. And probably could meet early in the afternoon if people want. And then Thursday and Friday can certainly have lots of time free. All right. So part A of the exam, that's the part that's like the midterm that is basically will cover Chapter 3 and maybe a problem from 4.1 and open notes and so on, but you can't get help from TAs or work with each other. It should be pretty short compared to the midterm. And so I'll post that tonight, and that will be due Thursday at noon. So this part of the exam really shouldn't take more than a couple hours at the most. Some of you might go through it very quickly. So hopefully everybody can get this in by noon. If something happens and you can't, let me know, but I'd love it if everybody got it in. I am most of the way through grading both problem sets 6 and 7. I'm sort of grading them in parallel for reasons I'm not quite sure. But I should have most of those back to you today. If you know that like you're planning on like doing the exam tonight because you want to get it over with or because you're so excited for it and you really want the your homework back, definitely tonight. Let me know and I can make sure to prioritize yours. I suspect I'm going to get most of them done, but not quite all of them before I give up and go home tonight. And then I'll get the rest in on Tuesday. So if you definitely want the homework today before I leave, which I can certainly do that, send me an email and I'll make sure to put it in your box before I go. OK, and then Friday, the last homework and part B of the final, which is a sort of mini project of some sort. Some of you have started them, will also be due. The homework for this week and part B of the final are definitely things many of you will want to get some help on. They're not easy or obvious problems. But hopefully they're fun and a good way to end the term by doing something difficult.
What time?
Oh, it doesn't really matter. No. Late is fine. Yeah. And I'll definitely have lots of time Thursday and Friday to help. I don't know that the TAs will have time this week, because I'm pretty sure it's week 10 for them also. Yeah, OK. And if these times don't work, just send me an email. I've got enough flexibility this week that I'm sure we'll be able to figure things out. Questions? Does that all make sense? Oh, you look so excited. All right. All right, so two things I want to do today. First, a little bit from 4.6, which is a super useful chapter on this thing called related rates, and then a little bit of review. So the problem that I thought I would work through as an example is sort of complicated enough to state that I included it on the list of problems sort of on the worksheet. So maybe I should pass these out. And I made more than usual, so there's probably one for almost every one of you. Maybe that's not. Here's one more. There.
Thank you.
All right. So. All right. So So let me explain the setup and a little bit what related rates are. And I think the best way to illustrate this is to just work through an example, then have you do an example. So here's the scenario. Suppose there's a 3-meter ladder leaning against a wall. And the ladder starts to slip so that it kind of goes down like this. And the question is, if you know the velocity here, how fast the base of the ladder moves, how fast is the top of the ladder moving? So there are two rates here, the rate at which the ladder is slipping down the wall and the rate at which the foot of the ladder is sliding along the floor. Does that make sense? Two rates? And you might think, well, gee, but they're not really two rates. They're related, aren't they? I mean, if I know how fast this is moving, this ladder, it's a rigid object. I must be able to figure out how that, I mean, that determines how this moves. There's sort of no choice. And if I know how fast this is sliding down the wall, that would determine how fast this is sliding along the floor. So there are two rates, but they're not really different rates. They're related rates. That's why we call these related rates. OK. All right, so then we might wonder, well, how are the rates related? That's where the calculus comes in. So there's a relationship between x and y and 3. Does anybody want to fathom what that might be? Excellent. Y squared equals 3 squared. So x squared plus y squared equals 9. So in a moment, we'll take the derivative of both sides of this with respect to time. So this is sort of and I almost think of this as like a doubly implicit function, in that x depends on time and y depends on time, and x and y depend on each other. So I'm going to take the time derivative of both sides of the equation. And that's a valid move. I can do whatever I want to an equation as long as I do it to both sides and as long as that thing isn't dividing by 0. So that certainly seems like a safe thing to do. So let's start with the right-hand side. That'll be easy. Derivative of 9. 0. Yep, that's good. All right. So what's the derivative of x squared with respect to t? I could if I wanted, I could write it like this to remind myself that x is a function of t. So then x is like an inner function. So that would be 2x times the derivative of the inner function, which is dx dt. And we'll have the same story for y. So now I can simplify this a little bit. The 2's go away. And let's see, the problem eventually, what is the problem eventually asking for? Knowing, I'm eventually interested in how fast the top of the ladder is falling. So I'm going to solve for dy dt. So let's see, let me do that. So y dy dt is minus x dx dt. So dy dt is minus x over y dx dt. All right, so I'm not going to try to convince you this is exciting, but I do hope to at least convince you that this has some utility. So we said here, all right, so this ladder is sliding down, and this is moving at some speed, and this is moving at some speed, but they're really not different rates. They're related somehow. And then you might wonder, well, gee, I wonder how they're related, and that's what we've just figured out. So this tells me if I know how fast x is moving, the foot of the ladder is moving, I know how fast the top of the ladder is moving, and conversely. So there's a relationship between the two rates, and now we know what it is. So that would be is a useful thing, and now we can just solve the problem by plugging in some numbers that are given. So we're told that the ladder moves, the foot of the ladder moves at an outward speed of 0.1 meters per second. OK, so dx dt is 0.1 meters per second. What else do we know? At that particular moment, x is 1. Well, we're going to need to know what y is. Any idea how we can figure out y? Yep, so let's see, what do we know? We know 9 is 1 squared plus y squared, so that tells me that y 8. All right, so related rates problems tend to work like this. You've got two things that are related. In this case, x and y are related by the Pythagorean theorem. And then you might wonder, well, how are their rates related? Well, if you know how they're related, you can figure out how their rates are related by taking the derivative of both sides of the equation with respect to t or whatever it is. And you'll have to implicitly differentiate. But then you have a relationship between the rates. So you're converting a relationship between the values to a relationship between the rates. So it may or may not seem like it, but a super useful thing in certain contexts. So there is a problem, second problem on your worksheet, which also happens to be a problem from your homework assignment, is also a related rates problem. Similar structure to this, a little bit more algebra, but let's spend a few minutes working through that. First, you'll have to draw a picture and figure out what's going on. And then we'll get a relationship, and then we'll turn it into a rate relationship, and we'll be psyched. All right, so I think the key to this one is to draw a nice big diagram. And I always draw diagrams bigger than I think I'm going to need, because I often need big diagrams when you start labeling things. So here's this hemispherical bowl. It's filled with water up to here. This is the height of the water. This is 10, the radius, so this is 10 minus h. This is also a radius of the sphere. And so we want to know the radius of the circle, smaller circle made by the water, by the surface of the water. So that would be this r. So it felt like when I was drawing this, people were nodding, if not happily, somewhat contentedly as I labeled these things. So then, there's a right triangle here. So this squared plus that squared is that squared. Solve for r and simplify. I FOILed this out. These hundreds went away. Was careful distributing the minus sign. I end up with this. Square root takes me there. So people feel OK about that? So what we did now is we said, hey, r and h are related. There's a relationship between r and h. So then the calculus comes in when we say, all right, I want to figure out how those rates are related. So to go from a relationship to a rate relationship equation, we take the derivative of both sides. So that's what I'm starting to do here. And I wrote r of t and h of t instead of r and h, just to remind you that h is really a function of t. If this seems cumbersome or you don't need reminding, then there's no need to write it explicitly as h of t. So now we need to take these derivatives, and then what are we ultimately solving for? We're solving for dr. Is that right? Mm-hmm. So I guess we are kind of, then we'll have a bunch of stuff on the right-hand side, and we can use information in the problem to plug in. So let's take a minute to get started on that, and then I'll finish it up, and we'll see how we feel about related rates. How about that? OK, a few people nodded. I'm going to take that as overwhelming assent. Let's go for it. All right. So we last left off where we had to take the derivative of both sides of this. So derivative of r with respect to t is just dr dt. That's what we'd like to find out. So then I need to take the derivative of this, and that's first a chain rule thing. So the derivative of blah to the half is half blah to the minus half. Then I need to take the derivative of the inner function. Derivative of h is, well, just the derivative of h, and the 20 stays, so it's a constant. Then this is chain rule or implicit differentiation. Derivative of blah squared is 2 blah. Derivative of the inner function h is dh dt. So it looks a little unwieldy, but it's all going to be OK. And here I just took the square root, brought it downstairs. So now we can just plug in. We're told that when the height is 5 centimeters, the water is falling at a rate of minus 0.1, or it's falling at a rate of 0.1. Its rate of change is minus 0.1 centimeters per second, hour, who knows? I think it was an hour in the problems. Yeah, so this is a very slowly draining thing. So then here I just started plugging in numbers. And I maybe skipped a few steps. If h is 5, 20 times 5 is 100. 100 minus 5 squared is 75. And then doing all that and noting that there's 2 minus signs here, which turn it into a plus. This whole thing becomes minus 1 over 2 square root 75. So the basic structure for related rates, you have a relationship, in this case between x and y, or here between r and h. And then you want to turn that relationship into a rate relationship. So you just take the derivative of both sides, and you end up with an expression like this that relates the two derivatives. And then if you wanted to know numbers, you could plug in numbers if you're given them. So super useful, believe it or not. Are there questions on this? Yes. Oh, you could say it's decreasing at a rate of blah, or its rate of change is minus blah. Yep, either way. Yep. All right. So the other thing I thought would be good to do today would be a little bit of sort of practice and review, motivated in part by my Odyssey grading homework 6 and 7 over the weekend. So I made 3 practice problems. These are similar to things that will appear on the part A part of the exam. And I thought the best thing to do would just be for you guys to try them, and then I could go over them. So, and you can do this in a group or individually as you wish. I made enough of these that there should be one for almost every one of you. So let me say just a couple of things I wanted to underscore with these 3 examples. I don't know that I have much to say about this unless you have questions. The main reason I wanted to assign this was it's a chain rule and then a product. And some folks were remembering the chain rule and forgetting the product, or the other way around. So you have to do both. So outer function is square root. Inner function is this thing, which is a product. So first you do the chain rule. Derivative of blah to the half is half blah to the minus half. And then you need to take the derivative of the inner function. And the derivative of the inner function is a product. Take the derivative of this one, leave that one alone, plus leave this one alone, take the derivative of that one. And that's all that stuff there. One thing I wanted to underscore is to be careful how you write these things, in that from here to here, I didn't take the derivative. I just rewrote it using laws of exponents. From here to here, I did take the derivative. And so sometimes people write this, they leave out, and they just do equals, 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 because like every step you put in equals. But all of these are equal, but this is not equal. When you take a derivative of a function, you've just made a new function. When you rearrange exponents, you haven't made a new function. You've just written it in a different way. So I think that can help, particularly for problems where there's simplification, and then you take a derivative, and then you simplify. Being careful how you write it can help you make sure you're thinking about it right. So anyway, there are two things you're doing. You're simplifying, or you're taking a derivative. OK, so here, again, I'm first going to just do some algebra to rewrite this like this. Then I take the derivative. I'm making a whole new function. And this is chain rule. And notice that the derivative of e to the minus x is minus e to the minus x. Because the inner function, right, is like this thing there in orange. So it's the derivative of e to the orange is e to the orange times the derivative of orange. The derivative of minus x is minus 1. So it's easy to forget this minus sign. Lots of people did it in the homework. Totally understandable. It's an easy mistake to make. But these are, it's barely an inner function. I mean, it's just minus x. It's, when it's something attention getting like this, like all the chain rule, alarm bells, flight or fight mechanisms, whatever it is, that triggers starts to go off. But here, you're not, maybe it's easy to overlook the chain rule because it's so innocuous looking. Similar story over here. So cosine 4 minus x, derivative of cosine blah is minus sine blah. Oh, but then there's a derivative of the inner function. The derivative of minus x again is minus 1, so those minuses conspire to make a plus. So there was a little bit of confusion on problems like this on the homework, and a bunch of confusion on e to the minus x. Yep, that's certainly fine. I mean, usually it's, if you then were going to have to do anything with this, you would probably want to rewrite it like this, because it's much more convenient. But yeah, there's no need to simplify. So there'll be a bunch of problems like the ones you just did on the final, and there's, all you need to do is take the derivative. You don't need to massage it into any particularly aesthetic form. So take a minute and do problems 2 and 3, and then we'll talk about those, and then we'll wind down. So this one, we're doing a local linearization near x equals 1. So that's a tangent line at x equals 1. So this is a nice formula for that. A is the point at which we're finding the tangent line. In this case, it's 1. So then I need the derivative. Derivative of natural log is 1 over x. 1 over 1 is 1. I also need to evaluate the function at 1. Log of 1 is 0. Why? Because e to the 0 is 1. In case that was harken back to the days of logs. And so then we can plug into this formula after doing it wrong. Here's the correct version. So 0 plus 1 times x minus 1. I end up with minus 1 plus x. So if somebody were to say, what's log of 1.1? You'd say, well, I have no idea. I don't know anything. How could I figure that out in my head? Oh, wait, well, gee, just moments ago, I did this tangent line approximation. And this is supposed to be in a good form if I'm near x equals 1. Well, 1.1 is pretty close to 1. So why don't I just plug into the tangent line approximation, and I get 0.1? And then maybe one wouldn't believe that. You could check on a calculator that the natural log of 1.1 is actually 0.0953. So that seems not so bad. Are there questions on that? The main thing I wanted to illustrate is what to do with a tangent line approximation once you have one. The point being is that you use it to approximate a function.
Below the f of x equals 0, blah, blah.
Yep.
Is that smudge anything, or is it just positive x minus 1?
That's.
Why do you have to change that to negative 1 of x? Couldn't you just keep it 0?
There's no reason. I guess it made me feel better. Mx plus b, b plus mx. I don't really know why I did that. So yeah, that's sort of what I was kind of thinking. But this answer, and these two answers are the same. So if you're happy with this, which I think I'm hearing that you are, then that's totally fine. I mean, these are the same thing. I don't know why I rewrote it like that. So tangent line approximation seems like a silly thing to do. Why would you want to take a curvy log and approximate it by a line? But it really is a useful thing. It comes up all the time. We've done it a lot in differential equations, this term. So anyway, that's that. All right, so lastly, just taking two derivatives of this function. This was something a number of people got twisted around on. There were a couple of problems where you had to do things like this. So the first part of this is just chain rule. So derivative of e to the blah is e to the blah times the derivative of the inner function. The inner function is minus cx squared, whose derivative is minus c2x, which I then rewrote like this just to bump everything out front. Oh, yeah. I did. It came back, but it probably never should have left. I think now it's consistently there. Sorry about that. Thanks for catching that. OK, so then you need to take the derivative again, since the second derivative is a derivative of the first derivative. And some of you maybe were in such a chain rule groove that you forgot to product rule. But this is now a product, right? There's a minus 2cx times a e to the minus cx squared. So here I'm taking the derivative of minus 2cx, and I just get minus 2c. C is a constant. And the second function, e to the blah, 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 stays the same. Plus, leave this function alone, take the derivative of this, which you've already done here. So here, this is the first function being left alone. The derivative of e to the blah is e to the blah, times the derivative of blah, the inner function, which is another minus 2cx. So I've got a minus 2cx, a minus 2cx. That becomes a plus 4c squared x squared, and there it is. Questions on that one? Do people feel energized and ready for the final and last part of the term? Okay. Well, I'm sorry to hear that. I've sort of said all I can say. I will. I mean, I think you're in good shape. I think you won't find the part A of the final is again very similar to what we just did in class here. I can stick around until a little bit before 3 for homework help or help of any sort. I'll be over in the dining hall after I return the microphone, and then whatever I said tomorrow 5 to 6 and perhaps earlier.